Good afternoon, everybody, and welcome to this sixth in a series seminar of Remade at ARI. Before I give the floor to Eric HIRSCHMANN for the presentation today, I would like to very briefly give you some information about our project in case this is the first time that you are attending the seminar. Remade at ARI is a EU-funded materials hub. Remade at ARI stands for Recycled Material Development at Analytical Research Infrastructure, and the project does exactly that, provide access to a large number of research infrastructure all across Europe to academia and industry stakeholders that need analytical tools in order to examine the properties of recyclable materials or develop new recyclable materials. The consortium is a partnership between a large number of European research institutes and universities, and in the core of the project is some of the prominent analytical research infrastructure of Europe, and you can find all the information about the project and the partners and the tools in the project website listed at the bottom of the slide. So today is a kind of a celebratory day for us because it's a 1-year birthday of our project. Remade at ARI turns 1 actually today. And we are happy to report that the project is in full swing, and all the services provided by the project are currently open, and we are accepting proposals in a number of different schemes, some specifically for academics, other for industries, for small to medium enterprises. So again, please do visit the website and find all the information and details and procedures for these services. So moving on now to our webinar today. As I said, this is a webinar series that has been going on since the beginning of the year. Each time we have a speaker from a different research infrastructure, and the scope of this series is to introduce the different tools, the different characterization techniques that are available in our consortium, and of course to teach and educate and inspire future users of our platforms. Each time we aim to give this seminar at the last Friday of the month, but this may vary. So please do check our announcements in social media for each seminar. And just to give you an idea of what has been seminar have been given in the past and what is to come in the future, this is a very nice graphic. The seminars that have been given in the past are available through our YouTube channel, so this is possible to attend them even now. Going on then to our first to our speaker today, we're very pleased to welcome Dr. Eric HIRSCHMANN that will give us a presentation on non-destructive material analysis using positron annihilation spectroscopy. So, Eric, the floor is yours.
Okay. Thank you, Mary, for the kind introduction, and happy first anniversary. So lucky to be part of Remade and be here at the seminar talking about non-destructive material analysis using positron annihilation spectroscopy. To give you a brief introduction in the field, for all of you who doesn't know what a positron is, this is the antiparticle of the electron, which means it can annihilate with the electron, and if so, then emits a characteristic radiation of 511 kiloelectron volt. And the positron as an antiparticle can be created via beta plus decay, so from radioactive nuclei, or via pair production in large-scale facilities or nuclear power plants. Nuclear power plants for sure. And for material science, we use positron as a microprobe to investigate materials and their properties. So how we do this, the positron itself is sensitive to atomic disorders or disorders on an atomic level. As you can see here, I try to use my laser pointer, so yeah, maybe. So as you can see here in the upper part of the image, there is a more or less perfect lattice, atomic lattice, and in the lower part, there is something missing. And here is missing the atomic core and the positron. So for you, it seems more or less the same, but for the positron, there's a huge difference in the, no, I can't. So now I can switch. Huge difference in the electronic, density. So if you remove an atomic core, also you remove the electrons in the near area, and therefore you create a negative potential where the positron can be trapped. And this trapping is more or less the key to investigate missing atoms, cracks, or even pores in the later phase. And due to the high sensitivity of the missing electron density in this area, the positron can detect up to 1 defect per 1 million atoms. So it's quite sensitive. How to define the life cycle of a positron? Usually you have the generation of the positron, which is, as I said, beta plus decay, or even with pair production. You have the implantation of the positron within the material, and this varies from the method you use to generate this. So it's up to 2 millimeter. You can implant the positron in the material, but if you vary a little, you can also investigate thin films of 10 to 1000 nanometer, but I will show you this later. After the implantation, there comes a short track of diffusion in the material, so up to 100 nanometer, and at the end it gets trapped in some kind of defect till it's annihilated or annihilates with an electron and emits the gamma ray. And the gamma ray is the information transmitter. So when or how this gamma hits our detector releases the information or the information about the material itself. So what information do we get from the positron? We have mainly two kinds of properties we measure. First of all, the positron annihilation lifetime, which is more or less the time difference between the birth and the annihilation. And this this helps us to investigate the electron density at the annihilation site. And this refers to the defect type, size, or the defect concentration. And the grayish part I will show you later after or within the discussion of the devices we use. But let's first focus on the annihilation lifetime or positron annihilation lifetime. How do we measure? So first of all, the implantation and the diffusion, and then it depends on the defect size. So the larger the defect, the longer the positron lives in the material. And this releases some kind of a individual property for single voids up to mesoporous materials, so in the range of 20 to 100 nanometers. So this 100 nanometers is more or less the maximum what can be investigated with positrons. So, and at the end, we measure some kind of histogram. This is called a positron annihilation lifetime spectrum, which is more or less a histogram of the time differences we measure. And then there are appropriate, sorted. And after that, we fit these decay curve with a sum of exponential decays, decay functions, and we got an intensity and also a lifetime from this. Here, for example, we measured porous glass with 5 positron lifetimes. So as you can see here, to fit this histogram or this positron lifetime spectrum properly, you need 5 exponential decay curves, each with an individual lifetime and intensity. And as you see, the tau 1 is referred to the mesopore of the porous glass in the range, and this leads mesopore, which means you have 91 nanoseconds, and this can be translated in up to 6 nanometer pore size, and also a second pore within the porous structure, which is then 31 nanoseconds, and this is then up to 2 nanometers, and so on, up to the atomic framework of the glass, and also some interstitial free volume, which is lower than 1 nanometer. So you can investigate a broad field of material properties if they are correlated somehow with the defect structure or the porous structure of your material itself. And as you see, you can get the lifetime itself, which is correlated to the defect type or the size, and you can get the intensity, and this is correlated to the concentration or the variation over within the material. And what else could be said? So each of these parameters, so lifetime itself and the appropriate intensity, can be correlated to certain properties of the material. Here, for example, we measured vacancy clusters in high purity elements. And as you see, for each element, you have, for the defect-free material, defined lifetime, which is, for example, for iron, 108 to 10 picoseconds. And if you create, for some reason, mono vacancies in this material, you create a huge step between the bulk or the defect-free material and the material with defects in it. And then you can see that the lifetime increases to the number of 175 approximately picoseconds. And therefore, you can distinguish between the defect and the defect-free material, and same for other materials as well. What else could be said? As I said, the intensity can also be used as a monitor for defect concentration. Here, for example, we measured the defect kinetics in stainless steel and measured the positron lifetime, or in this term, the increase of the defect intensity for an increase in the tensile load. So this is a standard stress strain test, and yes, you see in the first 5% of changing the length of this metal, the defect intensity increases significantly. And the same idea can be used to investigate the material properties of metals or plastics for cyclic load. Here, for example, we measured a nickel alloy, and as you see, for an increasing cyclic load, the defect intensity also increases in a more or less exponential manner. And yeah, this is for the metals and alloys. Same for semiconductors. If you have, for example, different dopants in the semiconductor, then, or this leads to some kind of defects in the material, positrons can help you to investigate them as well. What else? Switching a little bit the material coming from metals and semiconductors, now switching to polymers, or like soft matter. And as you can see here, positrons can also help to investigate the interstitial volume as well as the free volume here in blue and red. And for example, if you vary these, if you vary the temperature for these materials, then you can also see that there is a trend, and you can also see if this trend varies. You can define the glass transition temperature, for example. What else? If you increase the voids of pores even more, then you reach the size of nanopores, which are important for catalysts or carbon capturing or wastewater treatment. think in this direction. And what we can see here is that the positron lifetime is correlated with the pore diameter. And the model we use here is the extended Tau-Eldred model, which is well known for more than 20 years now. So this is a good tool to also investigate these kind of pores. And even if you have a closed pore system, which are hard to investigate with gas sorption or mercury intrusion, then you can also use this tool, because positrons, don't, they have no problem with walls, so they can enter also the closed pores as well. And the good point here is, if you have a porous system and would like to investigate the pore size distribution, then you can do this with positrons as well, just by calculating the pore size and using the positron lifetime distribution, and then calculating from this the pore size distribution and their fraction within the material. Here, for example, we have a silica gel investigated with different solvent concentration. And as you see, if you choose like 10% solvent concentration, you can manipulate the pore size distribution, as long as you wished for a high peak or broad distribution. This depends on the application you would like to see. Here's a list of other ideas you can have thinking about the application, or the positrons are useful for your science, or as well as for industry partners. So just to give a few here for have the observation of the behavior at different temperatures or relative humidity for bulk materials or powders, investigating filters or membranes, or just influence of the heat treatment on the microstructure, to mention some or a few. Otherwise, if you watch this on YouTube, just pause here, read it, and then you can have a look later. This leads to the technical point of view. Now, what can we do, or how it is done at the HZDR? First of all, we start with the more simplistic kind of method, which is the source-based pulse. So in principle, you need a source, which is here in the upper picture, the orange foil, and in the middle, or in the mid of this orange foil, there's a sodium-22 source, which emits the positron in your material with a high energy. So this is for bulk studies. And luckily, the sodium-22 delivers, besides the positron, also a 1275 kiloelectron volt start signal. So you measure the time difference between the start signal and the stop signal from the annihilation event, and then you get the positron lifetime and all the parameters I mentioned before. Coming to details of our setups, we have 2 setups at the moment, working with 4 tubes, which increases the solid angle and decreases the time per measurement. As I said, we could measure open and closed pores up to 100 nanometer. And the region of interest, which can be investigated with this kind of setup, is approximately 1 millimeter lateral and up to 2 millimeter in vertical range. But this depends highly on the density of the material. So high dense material stop the positron earlier, and low dense material need a thicker material or stops the positron later. So this for the positron. And now the parameter we can offer. At the moment, we have these 2 setups. Both are able to measure your material in situ from 30 Kelvin to 500 Kelvin. One of them is able to also in situ vary the pressure from like 1 or 20 millibar to 1000 millibar with or without different atmospheres. So you can use air or humidified water or CO2 or nitrogen. This is up to you and what gas we can offer at the moment. And for the other one, it's also possible to vary stepwise the relative humidity using a special chamber and a kind of saturated salt to vary these humidity in situ. Coming to the limitations, working with source-based pulse. So, for example, large geometries for the sample are not so good, because this will increase the measurement time and also, yeah, leads to some changes in our setups. Of course, you have to be aware of the radioactive isotopes. So this is not for your home. This is just for a specialized scientist or people with an appropriate training. If your system is quite complex, the analysis is also complex, but this is a point which is the case for all of other methods as well. As I said, we have an upper resolution limit for porous, which is 100 nanometer approximately. And yeah, the last point is for the source-based pulse, thin layers can't be investigated. So there is a limit of like 300 micrometers and lower. So be aware that if you would like to investigate thin films, you need another kind of positron method, which I will show you now. This is the first of our beam-based positron facilities, which is called MEPS, the mononegative positron source, which enables us to measure thin films in terms of 10 to 1,000, 2,000 nanometers approximately, depending a little bit on the density and on the atomic number of your sample. But in principle, this is the range we can investigate. And this is the setup in real. And here are the properties or the some kind of informations about this mononegative positron source, which is used for also defect depth profiling, which means we can here vary the energy or implantation energy of the positron, and therefore you can see stepwise or energy-wise what happens from the top to the substrate of your material within. And here we have a measurement time which is quite fast, which is 1 minute. I skipped this part for the source-based positron setups, we have it for source-based. It's approximately 15 minutes to 12 hours, depending on the resolution or on the details you would look at. And here you are complete a little bit faster, so 1 minute per energy or temperature, which is at the moment can be varied from 300 to 550 Kelvin. And we would like to upgrade this system in end of this year, but to be honest, maybe beginning of next year could be the good point. And then the temperature can be varied from 50 Kelvin to 880 Kelvin in situ for thin films. And I think this will be a quite huge change or upgrade for this kind of setup. And as I said, here is an example for this kind of measurement. Here's in the upper picture, you see a carbon film on top of a porous glass, and in the lower part, there's a graph showing the carbon intensity or the intensity we get from the positron annihilation lifetime spectrum, referring to the carbon, and this decreases over the implantation energy. So as you see, you can see what happens from the top to the substrate and investigate even thin films. Here, for example, a 280 nanometer film of carbon, which is just an example. Another point we investigated due to these fast measurements were the changes in materials with loaded hydrogen. So here you can see what happens if the material was loaded with hydrogen and what happens over like 10 hours. And as you see, the defect component increases due to the release of the hydrogen, and therefore the vacancy becomes visible again for the positron. And so we see an increase in this lifetime. For these kind of large-scale facility, there is also some kind of limitations. First of all, this is mandatory to have a beam time proposal if you go the normal way, or you can use, here is the link to Remate, use the possibilities Remate offer you to get a more or less easy access to this device and use it in a more simplistic way, or without the strong limits given by the normal way. So there is to sum it up, it's easier if you use remade compared to the normal way if you would like to measure some kind of material which are connected to circular economy. Other limitations is the sample size. So the sample should be, in the best case, 10 times 10 millimeters. So it fits properly to our sample holder, and there is no lateral scan because the beam spot is approximately 4 millimeters and not larger or smaller. So be aware of this. But as I said, the depth or the energy, the implantation energy can be varied, and therefore the depth profiling can be done with this machine. And in addition, your samples should be vacuum stable. The next one is a combination of two setups with a new kind of method. So this is the sponsor in the left side. So the slow positron system of Rossendorf, and on the end part of the station there is the AIDA, which stands for apparatus for in situ defect analysis. And with this machine you can, first of all, the machine in reality, as you see, this is kind of an facility with 4 germanium detectors and the beamline in between. But if you like, you can also visit HZDR and can show you in reality. But what I would like to tell you is the method behind the setup. This is called positron Doppler broadening, which measures the annihilation spectrum, so the energy spectrum of the annihilation event. And this could be used to investigate the electron momentum transferred to the gamma release during the annihilation event. And this leads to some information about the defect decoration, defect concentration, or the relative porosity. In terms of, as you can see here, this is the energy spectrum for this kind of Doppler broadening measurement. In the graphic, you can see in the left side, or first of all in the right side, there is the 511 energy peak, which can be broadened if you have less or more vacancies in your system, or gets broadened if you have less vacancies in your system. So we calculate the S and W parameter, and the S parameter is more or less correlated to the defect concentration, and the W parameter is correlated to the defect decoration. And this leads to more and more information about your material and the surrounding atoms, or the atoms surrounding your vacancies, for example. And the third parameter you can see here is the so-called 3 gamma to 2 gamma ratio, which is placed in the middle of this energy spectrum. And this is an indicator for the release of, or is an indicator for porous structure, or an increase or decrease of pores in your system. So you can do both, but what you can't do is you can't measure the positron lifetime. But nevertheless, same procedure. You can investigate thin films with this machine up to 2000 nanometer. You can do the depth profiling, so you can also investigate layered systems. You can investigate the defect environment, as I said, using the W parameter, and also the defect concentration. And for the apparatus for in situ defect analysis, we have some kind of extra beams within. So for example, we can use MBE, so molecular beam epitaxy. We can use ion implantation. We can vary the temperature for even higher values, so up to 1370 Kelvin. And we can do also for virus sensing in situ during the positron broadening measurement, or positron annihilation measurement. So what else? As I said, you can also only do Doppler measurements, which means all the information from positron lifetime can't be gathered, but all the information from the Doppler broadening, which I mentioned before, you can't, same to maps, do no lateral scan, so the beam size is more or less the same. The measurement time here is approximately 20 hours or 12 to 20 hours per sample, so the full scan. And also you have a limit to the sample size. It's better to have a 10 times 10 millimeter sample, larger as possible, small as possible, but it depends a little bit on the ability to, or on how we can place the sample on our sample holder. At the end, coming to the a little outlook for our work in progress, which is our in situ fatigue analysis. As I said before, we have these measurements for the stress strain or cyclic load measurements, which were done ex situ, but we plan to do this within the next 2 to 3 years in situ with a special cyclic load machine, appending it with the positron lifetime, and have these curve on one and the same sample without cutting these into pieces. And this brings me to the end. If you tell someone about this talk, then just summarize it as pulse is an innovative and non-destructive method for the qualitative and quantitative analysis of material properties on the nanometer scale. And with this, hopefully you enjoyed the seminar, and I'm open for questions.